So another weird phenomenon that was observed in the 21st century was the photoelectric effect, which consisted of shining light on certain materials and observing current flow, otherwise known as the material ejecting electrons. And one of the properties of the phenomenon was that there was a minimum or threshold frequency before we would observe any electrons being emitted. So you can imagine that I could have a block of any material really, but usually consisted of a metal. So let's suppose I had a block of zinc and I shone a red light at this block. Red light has a low frequency. It's a low frequency light. And so in this case, we'll say that the threshold frequency was not reached. So this block would not emit any electrons. I could increase the intensity of this red light, which simply means sending more red light at the block, and still no electrons would be emitted. If I increased the frequency of my light, so instead of red light, I am now emitting blue light at the block, a single ray of blue light, which is high frequency, will begin to make the block emit electrons. If I increase the intensity of blue light, then I am simply emitting more blue light at the block, and it will still emit more electrons just because I increased the surface area of where I'm emitting the light. In other words, the parameters for this phenomenon depend solely on frequency. If the frequency of the light is not met, no electrons will be emitted. If the frequency is met, then increasing intensity of light, or increasing the area or surface area of where your light is interacting with the material, that will also increase the amount of emitted electrons. Of course, if you increase your frequency beyond the threshold frequency, increasing frequency beyond the threshold frequency will result in more electrons being emitted, and increasing your intensity after or given that your threshold frequency has been reached will also result in more electrons being emitted. So just to reiterate, if you're below the threshold frequency and you increase the intensity of your light, no electrons will be emitted. To explain this phenomenon, which was never observed before, we required the invention of the photon. So Einstein invented the photon and explained that light is both a wave and a particle at the same time. And its particle nature came from Planck's quanta. So Planck said that energy was discretized, or it came in packets, and these energy packets, Einstein said, could be thought of as particles with the names of the photon. And these photons compose all electromagnetic waves, and they are particles that have an energy equal to the energy of one of Planck's wave quanta. So its energy is equal to hf. And it was these photons, or the collisions between photons and electrons, that caused the electron to be ejected. And so it's the photon that is responsible for the photoelectric effect. So we explain the effect in saying that if we have even a minimal amount of photons that are high energy, in other words, they're high frequency, they come from high frequency light. So if we have even a small number of these photons with large energy, they will eject the electrons that they interact with or collide with. If we have low energy photons, so low frequency wave photons, then they don't have enough energy to eject the electrons. Not enough energy to eject electrons. And you can increase the number of these photons, but still the interaction of the photon with the electrons will still result in no ejection. So increasing the number of photons you have does not result in the ejection of electrons. In other words, intensity of light is only a factor if and only if the threshold frequency has been met. The way the effect actually works is that we can imagine that our material is composed of several atoms, usually metallic atoms. And if we zoom in at one of these atoms, it's going to have electrons around it. Of course, electrons are negatively charged, and the atom's nucleus is positively charged. So there is an interaction over here where the electron is attracted to the nucleus, and it has some energy that is called the binding energy. So this energy is what keeps the electron from flying away from the nucleus. So this binding energy is also sometimes called the work function of the material, or W for short. And the work function differs between different materials. So the work function of sodium is going to be different from the work function of zinc, which is going to be different from the work function of gold. And the way that the photoelectric works is that we're going to have a minimum threshold energy. We're going to have an E threshold, which is equal to the binding energy, or the work function of our material. So we'll write the work function instead. We're going to have an E threshold, which is equal to W. If our photon that collides with the electron has more energy or equal energy to this threshold energy, it's going to eject the electron. So if photon has E that is greater than or equal to W, or the threshold energy, then we eject the electron. If it has less energy, then the electron will not be ejected. And any excess energy, so if we have more energy than the threshold energy, then this will be transferred to the electron in the form of kinetic energy. And the way we can write this as an equation is that the maximum kinetic energy of the ejected electrons follows the equation Ek is equal to whatever the energy of the photon that is colliding is minus the work function of the material. So if our photon is coming in with an energy that is equal to the work function of the material, the ejected energy is going to be 0, or it's going to be very low. So we barely eject the electrons. If the energy of the photon is really high, then the electrons are going to be emitted at a very high speed, or with a very high kinetic energy. So the more common way to write this equation is Ek, which again is the maximum ejection energy, is equal to the energy of a photon, which is given by Planck as hf, or Planck's constant, times the frequency of the light that the electron is coming from, or the photon is coming from rather, minus the work function of the material. now an example, we have blue light, which is 400 nanometers for its wavelength, being emitted towards a block of zinc with a work function of 1.75 electron volts. And we want to find the maximum possible kinetic energy of the ejected electrons in this case, assuming that they are ejected. So we'll use our equation. We know that the kinetic energy, or the maximum kinetic energy, is equal to the energy of the photon, or hf, minus the work function of the material. H is Planck's constant, or 6.63 times 10 to the negative 34 joules seconds. Our frequency we can find by using our equation for all waves. So we know that the speed of a wave is equal to its frequency times its wavelength. For light, the speed is c, and so the frequency is going to equal c divided by the wavelength. So we'll have c, which is 3 times 10 to the 8 meters per second, divided by the wavelength of our light. We want to use SI units, so it's going to be 400 nanoists times 10 to the negative 9 meters. And then we're going to subtract the work function, which in our case is 1.75 electron volts. Now, before we can actually calculate this, we notice that over here, our equation is in joules, since seconds is going to cancel with this seconds, meters is going to cancel with meters, so we're ending up with joules. But on the right-hand side, we have electron volts. And so to keep everything consistent, we can either transfer electron volts to joules or joules to electron volts. And we know that we're going to get a small answer if we convert to joules, so we're going to go to electron volts. So 1 electron volt is equal to 1.602 times 10 to the negative 19 joules minus 1.75 electron volts. So now our final answer is going to be in electron volts. And if you plug that into your calculator, you'll get a final answer of 1.3578 electron volts. So the maximum kinetic energy, in this case, where we shine blue light at a block of zinc, the maximum kinetic energy of the ejected electrons is 1.3578 electron volts. Now we notice in this case that this amount is greater than 0. So since the kinetic energy is greater than 0, then we're emitting the electrons with some velocity, so they are ejected. If it was equal to 0, if our kinetic energy equaled 0, that means that our frequency is equal to the threshold frequency, and so we barely eject the electrons. And if it's equal to less than 0, that means that the energy of the photon minus the energy of the work function is a negative number, which means the photon had less energy than the work function, and so F is less than the threshold frequency, and we don't eject any electrons. So that's useful to know for these questions to see if or whether if the electrons are actually ejected. So since light could be viewed as a particle and a wave at the same time, Debroghlie suggested that perhaps all particles could also have wave-like properties. To show this, he used 3 equations. So we know that the energy within a particle or photon in a wave is equal to Planck's constant for a quanta, or hf. According to Einstein, all matter that had mass had an intrinsic energy equal to mc squared. And the frequency of any wave is equal to its speed, and we're talking about electromagnetic waves here, so its speed is going to be c, divided by the wavelength, or lambda. And so, if we start with the first equation, we have the energy of a wave, or a quanta within a wave, is equal to E equals hf. And we know that the energy of a particle is equal to mc squared, which is equal to hf. So now we just connected the property of the energy of a particle with the energy of a wave, or a quanta within a wave. And this is known as the wave-particle duality. Since we've connected the properties of both in a single equation, we've unified them. And then, to finish off the equation, we'll express the frequency of the wave in terms of its speed and wavelength. And we'll isolate for the wavelength by multiplying to the other side. So we get that lambda is equal to hc divided by mc squared. And then one of the c's cancel out. So lambda is equal to h over mc. And to generalize for all objects, the speed that they're propagating at is simply the speed that they're traveling at. So we get Debroglie's wavelength for all matter is equal to Planck's constant divided by the mass of the object times the speed that it's traveling at. And you might see this expressed as Planck's constant divided by the object's momentum. So essentially, Debroglie showed that all matter, so the tennis ball that you use to play tennis or the car that passes by your house, all of them also have waves. But since Planck's constant is very small and the masses of these objects are relatively large, these waves are not noticeable. But when we get to very small masses, such as for electrons, then this wave does become noticeable and we see its effects in real life. So now a question, we're asked to find the Debroglie wavelength of a tennis ball weighing 60 grams after being served at 70 meters per second. So we know that our equation for the Debroglie wavelength is equal to the Planck's constant divided by the mass and velocity of the object. We're given all this information, so we can instantly plug in. So we have 6.63 times 10 to the negative 34 joule seconds being divided by the mass of the tennis ball, but we want to stay in SI units, so we're going to convert it to kilograms. 60 times 10 to the negative 3 kilograms multiplied by the speed of 70 meters per second. If you plug that into your calculator, you'll get an answer for the wavelength of 1.58 times 10 to the negative 34 meters. So you can see that it's very small, which is why you don't notice this effect in everyday life. However, if our tennis ball was an electron and had a mass at the order of magnitude of 10 to the negative 31, then the wavelength would be much larger and certainly noticeable. And just to analyze our units to show how we get an answer in meters, we have joule seconds. Seconds at the bottom here being divided comes to the top. So we have joule seconds squared divided by kilogram meters. A joule is a Newton meter. Second squared divided by kilogram meters. So these two meters cancel out. A Newton is a kilogram meter per second squared multiplied by second squared divided by kilograms. So these two seconds squared cancel, these two kilograms cancel, and all we're left with is meters.